Okay, so I want to go through in this video and really focus on circuits. I'm going to kind of do it in a cartoonish mode, so you'll see here in a little bit what I mean. I found over the years this kind of helps explain what's going on with potential and current. So it's not, don't be offended when I'm doing it this way. I do it in my upper level physics courses. So I'm trying to go through and really get you to kind of understand the concepts of circuits. So when we're going to circuits, we're going through and starting to look at current electricity. Up to this point, we've been looking at static. So we're looking at electrons that are flowing. Okay, so we're looking at flowing electrons. And current itself, which is equal to capital I, is equal to the rate of flow of currents. So if you think of a river, you have a river flowing, we talk about the current of water, we're looking at the rate the water is flowing. If it's a high current, low current, so it's going to be analogous when you look at a river versus electricity. Current is going to be the same, where in water, we're looking at water molecules, the rate that water molecules are going down the river. In electricity, we're looking at the flow of the electrons. Sorry, that should be electrons. Got ahead of myself here. So we're looking at the circuit. So for a basic circuit, the first thing we need is a power source. In this case, we're going to use a battery. And we'll get into AC circuits later on. And we have a positive end and a negative end. Just a reminder, or not necessarily a reminder, some of you, if you've never taken batteries out of a flashlight, you should always hook them up positive to negative. Do not do this. Okay, that is dangerous. It's going to overheat. And also, don't hold your battery. So if you have a battery and you have your thumb here and you have your fingers here, what's happening is the current is going to start flowing through your fingers, and your tips are going to start getting warm. Okay, because you have the electricity starting to go through you. With a battery, just to kind of, a lot of you do not buy batteries anymore. So when you go to the store, you will see AAA, you will see AA, you'll see C batteries and D batteries. All of these are 1.5 volts. This is a potential that they have. If you take a multimeter, you'll actually see where they're about 1.8 volts. And by the time they get down to about 0.8 volts, they're dead and you can't use them. So when a battery dies, most of the time it's not down to 0 volts. What happens is they're not efficient and they're not putting out enough energy for them to be efficient. It takes more energy for them to pump the electricity out as it does to actually produce the energy. So let's go back to our circuit. So we have a battery, we have a power source. We're going to need some conductors, so we have some wires. So in other words, we're going to have metal and not plastic. Okay, you're not going to see plastic. You may have plastic or coating, so they may be coated, but the inside of them is going to be metal to allow the electrons to flow through. So you have a conductor versus an insulator. So the electrons flow slowly or is more challenged, whereas the electrons here flow easily. Okay. And then we need to have a resistor, is what we call them in physics. So something in the circuit. A lot of times for us, we're going to talk about a light bulb. This is really a resistor. It's going to use that energy. So a little close up the light bulb. If you've never had a light bulb blow in your house, so you have the tips here, you have the coils here, and a little metal part right here. So this is generally a black polymer or rubber, and then you have this little metal part. So the circuit's going to come in and hit here on the side of the coil and come out the bottom. But what you have inside is a coil that comes through. And a lot of times when a light bulb blows, depending on if it's not an LED, if it's an old-fashioned light bulb that blows, this breaks apart here, And when it breaks apart, the circuit is broken. So now the circuit is broken. And what happens is the current stops flowing and the light bulb's dead and doesn't work. And what was great about the old-fashioned light bulbs is you would see this piece of metal in here floating around, and you knew your light bulb was dead. You could shake it against your ear and you could hear it rattling. The LED lights and stuff like that are not as effective as knowing if they're dead or if something else is wrong. So when we're looking at our circuit, for our circuit to work, we need to have a closed circuit. Okay, so again, this is an open circuit. And we need a power source. Now we're going to talk about DC, which will be the battery. So this is direct current. And these are batteries, generally. For a short-term use, the current is going to be constant. And we know the currents, the potential in the batteries die out. But for a short term, it's going to be constant. And AC, alternating current. This is what's coming out of your walls. Okay, so when you plug in, you have your two prongs here. You plug something into the wall, that's AC. So the current is oscillating back and forth. So we have to have a closed circuit, we have the power source, and we have to have something, like a resistor, that's going to use this energy. So, and again, for us, we're going to talk about light bulbs, and that's where we're going to kind of focus and not get into the formal nomenclature. So what we're going to do next, in the next video, is we want to go through and look at these series and parallel circuits and how we're going to use Ohm's law to study these circuits. Now, you really want to pay attention. A lot of you are going to use Ohm's law in your circuitry. Believe it or not, in health professions, you're going to use Ohm's law to study these circuits. And you need to know current. Several years ago, I had a physical therapy appointment. And I had my arm here. And I was going to have electrical stimulation on my elbow. So they were going to put a probe here and a probe here and run electricity through my elbow. Well, they thought it was tennis elbow. And the lady told me that they were going to give me 3 amps. So my current was equal to 3 amps. Just a little side note, 1 amp kills. So 3 amps would have blown my arm off. So I'm like, are you sure you're going to give me 3 amps? She's like, yes, ma'am. I'm like, are you absolutely sure you're going to give me 3 amps? And I started pulling my arm away. And when she finally read the units, and it was 3 milliamps, which is still pretty high. But how important are these units? Had she given me 3 amps, my arm would have been blown off. I probably would have been killed. At the minimum, my arm would have been blown off. So units are going to be very important. And understand electricity will also be very important. Electricity can kill you. Amps and current, just a little bit is dangerous. So potential or voltage is going to be that energy bundle, that potential energy. What is that energy that the light bulb is going to use to create light? And so that's where we're going to go into circuits. So next video, we're going to look at series and in parallel, and we're going to use Ohm's law to analyze these circuits.